All right, so we're going to intro in with some knowledge about acids and bases and a little bit of new information that you need to know. So first of all, we don't just have acids and bases, we have what are classified as strong acids, strong bases, weak acids, and weak bases. And you need to be able to identify them as part of the course. And so how we identify them is pretty simple. If you take a look at this list right here for strong acids, there are only 6. And this is actually found in your data booklet, so this is not a chart that you have to memorize or a list that you have to know off by heart, although many of you probably will end up getting to that point. It's found on page 2 in your data booklet. Right down at the bottom, you can see there's a little chart that I've made that's just labeled strong acids. There's 6, and there's only 6. There will never be 7, there will never be 5, there will always be 6 forever and ever. And what we know about strong acids is that they ionize 100%. So that means that if you remember when we talked about dissociation and ionization equations, if I stick a strong acid into solution, it is 100% going to ionize. So for example, I take 100 hydrochloric acid molecules and I put them into water. Essentially all of them are going to turn into ions. Whereas weak acids, which are defined as basically any other acid that's not part of this list of 6, are all considered weak acids. These guys all ionize less than 1%. So if I were to take, for example, vinegar, which is a weak acid, it's not part of this list, CH3COOH. That, if I were to stick it into water, say 100 molecules of CH3COOH, maybe one of them would turn into ions. The others would just remain as CH3COOH in solution. And so because only maybe one would ionize, if you're lucky, then you're going to have a pH that's going to be a lot higher compared to strong acids that are going to have a really, really low pH. And it's just simply because the concentration of H+ ions that are going to be made for strong acids is going to be a lot higher than it is going to be for weak acids. For strong bases and weak bases, the definitions are a little bit different. For strong bases, there isn't like a set list or number of them that we give. We just kind of simplify the definition by saying if it's a compound that contains hydroxide in the chemical formula and it's soluble in water, then that's going to be a strong base. So things like sodium hydroxide, barium hydroxide, ammonium hydroxide, these are all strong bases. A weak base is going to be any compound that doesn't contain OH- in the chemical formula, but when you put it into water, it's going to make hydroxide ions in solution. So that's the definitions for these 4, and we're going to kind of look at these, and these definitions lead us into our next concept, which is Arrhenius Theory and modified Arrhenius Theory. So stick with me for the next clip, we're going to keep going. Another concept for acids and bases here is these terms called monoprotic and polyprotic. And so mono, if you remember, just means one, and poly means many. And so for acids and bases, we can have acids that contain 1 hydrogen in them, or we can have acids that contain more than 1 or many hydrogens, like these ones here. And so these acids here would be considered monoprotic acids, and these acids here would be considered polyprotic acids. We can also have monoprotic bases that have 1 hydroxide in the chemical formula, for example, like sodium hydroxide or lithium hydroxide. And we can have polyprotic bases that would have more than 1 hydroxide in their chemical formula. So things like barium hydroxide or strontium hydroxide. So that's all you need to know about monoprotic and polyprotic acids and bases. We're going to take a look at this theory that we've been looking at a little bit, kind of give it a name, and then look at some modifications that were made to it. So we've learned about acids and bases, and we've learned about 2 types of evidences. We learned about empirical evidences, and we've learned about theoretical evidences. So empirical evidences are things that we can use to detect acids and bases using our 5 senses, so smell or taste or touch or things like that. And then the theoretical evidences are what we kind of think acids and bases are made of. And so this original theory that was kind of proposed was And what we've used to kind of describe acids and bases is that acids contain H+, and bases contain OH-. So if you think of, for example, hydrochloric acid has HCl in its formula, it's got an H in it, that makes it an acid. We've got bases like barium hydroxide, Ba bracket OH bracket 2, or sodium hydroxide, NaOH. Those compounds contain OH- in them, and so those would be bases. What turned out for this theory, though, is that it seemed to be quite limited in its ability to describe acids and bases, because there were some compounds that didn't contain, for example, OH-, but still yielded a basic solution when we mixed it in with water. Would give a solution of pH of, say, 10 or 11 or something like that. So we knew that there was OH- ions in the solution, but the compound itself didn't contain OH-. So there were some modifications that we had to make to this theory, and so hence what we ended up with, which was called the modified Arrhenius theory. So the original theory was just called the Arrhenius theory. The modified one, obviously called the modified Arrhenius theory. And what it states is that simply that acids don't just contain H+, but they actually make a compound called hydronium, which is denoted as H3O positive aqueous in solution, and bases make OH- in solution. So it's not that they just contain OH-, but they make OH- in solution. And so these are the modifications that were made to kind of help encompass a little bit more of the acids and bases that are out there, so that the theory was a little bit more comprehensive and complete in describing acids and bases as a whole. So what I'm going to do in the next clip, stick with me here, is go through a couple of examples of what this means. How do we get H+ into hydronium, and how does this all occur? So I'll be right back. So just a little bit of a recap. Up here at the top, as we've talked about modified Arrhenius theory, our whole guiding principle here for acids and bases, and when we're writing these chemical equations down, is that acids make hydronium in solution. So the minute that we have an equation that shows that hydronium is a product, then we know that we're finished. For bases, the guiding principle is that they make hydroxide in solution. So the minute that we have an equation that shows that we have hydroxide as a product, then we know that we're finished as well. And so these are the guiding principles that you kind of gotta keep in the back of your mind, because there's no real kind of set way to kind of do this robotically. You have to look at what you have, look at the information that's there, and then say, okay, this is an acid or this is a base, and so this is going to make hydronium, this is going to make hydroxide, and so what am I going to do to make this happen on the paper? So I'm going to show you some examples of kind of some guiding things, some guiding questions that you can ask yourself to sort of guide yourself through the process of being able to do this. So the first one is, let's take a look at acids. So if I take an acid, let's say HCl, and I drop it into solution, what we've learned so far is that this is just going to ionize. It's going to ionize into H+ and Cl-. And we've written these ionization equations. Here it is right here. So that's kind of the first step. What we did with Arrhenius theory was we just kind of stopped there. We said, hey, acids make H+ in solution, or contain H+ in solution. And that was kind of where we stopped. But what we now know is that it doesn't really stop there. What we now know, according to the modified Arrhenius theory, is that H+ interacts with the H2O molecule that's in the water. And a little reaction occurs where we have H+ reacting with H2O to make hydronium. And all that's really happening here is the H positive is attaching itself to the water molecule, thus changing the water molecule into H3O positive. And so this kind of shows the process of how that happens in two simple steps. You can kind of see what happens. We've got HCl makes these two things, and then this H+ reacts with the water to make hydronium. But we can illustrate this in one step. And so we don't need to write those out as two steps. What we can do instead is we can go HCl plus water makes hydronium and Cl-. And so all that's happening here is this H+ attaches itself to the water molecule, just leaves the hydrochloric acid and attaches itself to the water, making the H3O positive here and leaving the Cl by itself. And because hydrogen left as an H positive, this Cl is going to be a Cl minus in the solution. And so that's how I get my products out of that. And that's all you got to do for acids. Acids is a one-step process, either a strong or a weak acid. You just take that acid, you react it with water, it makes hydronium and the anion that that acid was made from as well. And that's it, you're finished. So you can see that I've got H3O plus here as a product, and that's where I say, okay, hey, I've got a reaction here now that shows that I've got hydronium, so I'm done. If you come over here to bases, there's two different things you got to do here for bases. Bases can either be strong or weak bases, and the strong bases are really simple and really easy. All you got to do is write a dissociation equation for that. So you can see I take NaOH and I put it into solution. It's going to dissociate into its ions, Na plus and OH minus. And that's my guiding principle, right? Once I have a base and I have an equation that shows that it makes OH minus in solution, I'm done. And so I've got NaOH aqueous turns into Na plus and OH minus. We've written lots of those dissociation equations. That's it, I don't need to go any further, I'm finished. And so that's my equation for strong bases. Again, this is just one step. There's no multiple steps here. But for weak bases, it is kind of it's a two-step process. So if I take this weak base, which is in this case sodium carbonate, Na2CO3, I put that into water. First, it's going to dissociate. And so I've got two sodium ions here and a carbonate ion here. And I can show that through this first step right here, this dissociation equation that I've written down. And you can see that I've got the ions balanced, the states of matter, and the charges all listed appropriately. But what I do at this point is I have to take the anion, and you will always take the anion at this point. So in this case, it's CO3 2 minus. And I take that CO3 2 minus and I react it with water. Again, just like I did over here with the acid example, these acids and these bases are being placed into water, and water is a key component here in making sure that we're either getting hydronium or hydroxide in the solution. But unlike the acid equation that you can see where the water is taking the H+, in this instance, you can see that the H2O molecule is giving an H+ to the CO3 2 minus. And so what happens then is, because the CO3 2 minus is taking an H, and the H has a positive charge on it, that's changing this 2 negative charge to a 1 negative charge. And we're sticking an H on the front. So we have HCO3 minus aqueous. And because the water lost an H and a positive with the H, this just leaves an OH minus behind, and that's what I'm looking for, is the OH minus. So that's how I get this. Now, probably the question you're asking yourself is, okay, well, there's got to be some sort of basic set of rules that I can follow, and here they are right here. So first thing that you want to make sure that you do is, if you're ever given a compound and you're asked to write an Arrhenius theory or modified Arrhenius theory equation for it, first thing you want to do is you want to ask yourself, is it an ionic compound? Because if it's an ionic compound, you need to write the dissociation equation for that first. Then in the question, it will always state for you whether it's an acid or a base, or it'll give you some information that will indicate to you that it's an acid or a base. So it might give you the pH. So if the pH is 10, you know it's a base. If the pH is 4, you know it's an acid. Or it might give you, for example, a litmus test. It might say, hey, litmus has turned red here, which means it's an acid, or litmus has turned blue here, which means it's a base. And so once you know that information, you know whether it's an acid or whether it's a base, then you can write an equation that makes the appropriate substance, either hydronium or hydroxide. So if it's an acid, then I'm going to come over here and I'm going to follow these steps. If it's a base, then I want to say, okay, is it a strong base or a weak base? If it's a strong base, then I'm just going to do this over here. If it's a weak base, then I've got to do this two-step process right here. All right, and you can always go back and rewind this video, rewatch as you kind of work through the practice questions. And that's it, guys, for modified Arrhenius theory and the equations that you need to write. So good luck and thanks for watching.